Today we're going to continue with section 10.4, which is used inscribed angles and polygons. Earlier in the chapter, we learned that the measure of a central angle is equal to the measure of its intercepted arc. Over the next couple lessons, we're going to look at other angles formed by segments and lines intersecting circles. For today, we're going to look specifically at inscribed angles. An inscribed angle is an angle whose vertex is on a circle and whose sides contain chords of a circle. So here, angle ABC is my inscribed angle. Its vertex B is on the circle, and its sides AB and BC contain chords. Remember, the side of an angle is a ray, so ray BA and ray BC both contain chords. The intercepted arc is the arc that lies in the interior of the angle and has endpoints on the angle. So in this picture, the intercepted arc of inscribed angle ABC is arc AC. So the question is, how are inscribed angles related to central angles? So for example, if this angle 1 was 50 degrees, and this diagram should look familiar. We actually did problems like this earlier in the chapter. If angle 1 was 50 degrees, and that's a central angle, we know that its intercepted arc is also 50 degrees. Now we want to know how angle 2 is related to that 50 degrees. The 50 degrees is the intercepted arc of angle 2. We can work with the triangle here. This is an isosceles triangle because every radius of a circle is congruent. So we can do this two different ways. If this is 50 degrees, this adjacent linear pair angle is 130. So then angle 2 would be congruent to the third angle of that triangle. So if we do 180 minus 130, we get 50. And angle 2 and this other angle, which are congruent, each have to be half of 50, which is 25. We can also look at this with the exterior angle theorem that says if angle 1 is 50, since that's an exterior angle of the triangle, these two non-adjacent angles would add up to 50, and since they're both congruent, they would each be 25. Let's do this in the general case where the angle 1 is x. Measure of angle 1 is x degrees. Since that central angle is x, this arc is also x. And now, again, this is an isosceles triangle, and these two base angles must be congruent, so they must add up to the measure of the exterior angle, which is x. If these two congruent angles add up to x, each one is half of x. We have a theorem that says the measure of an inscribed angle equals 1/2 the measure of the intercepted arc. Another theorem. If two inscribed angles of a circle intercept the same arc, then the angles are congruent. Here we're looking at angle DAC and angle DBC. Those are both inscribed angles with their vertices on the circle, and they both intersect the arc DC. So let's say that that arc was x degrees. The first theorem says the measure of an inscribed angle is half the measure of the intercepted arc. So angle A, angle DAC, has to be 1/2 of x. And angle DBC, which also intersects this arc of x degrees, is also 1/2 of x. Those two values are the same, so by transitive property, the measure of DAC is equal to measure of DBC, and the angles are congruent, as stated in the theorem. We have inscribed angles, and we also have inscribed polygons. We've talked about inscribed triangles earlier in the year. Inscribed polygons are polygons where all vertices lie on the circle. When you have an inscribed polygon, you have a circumscribed circle, the circle that contains the vertices. So in this picture, we have an inscribed triangle with all its vertices on the circle and a circumscribed circle going around it. Here we have an inscribed quadrilateral with a circumscribed circle. Another theorem. If a right triangle is inscribed in a circle, then the hypotenuse is the diameter of the circle. Conversely, if one side of an inscribed triangle is the diameter of the circle, then the triangle must be a right triangle and the angle opposite the diameter is 90. This comes from the inscribed angle theorem. So if we look here, there's an inscribed angle, angle A, B, C, and we see that AC is a diameter. The inscribed angle intercepts the arc from A all the way around to C, which is a semicircle because of this diameter. So the measure of the inscribed angle has to be 1/2 the measure of the intercepted arc. Every semicircle is 180 degrees. So the measure of angle ABC must be 90 degrees. This has to be a right angle, and triangle ABC must be a right angle. Another theorem, a quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. If we look at this quadrilateral, we can look at a pair of opposite angles. I have angle EDG here, and since that's an inscribed angle, the measure of angle EDG would be 1/2 the measure of its intercepted arc, which goes from E around to G. I'm going to name it with 3 points here. And then we can look at the angle that is opposite to it, angle EFG. That inscribed angle is going to be 1/2 of its intercepted arc, which starts at E, goes through D, and goes to G. We want to know what happens when you add these two angles together. When I add these two angles together, I get that the measure of the two angles, the sum of the measures of the angles, is equal to the sum of these arcs. If I factor out this 1/2, I see that it's half the sum of these two arcs. And if we look at those two arcs, EFG plus EDG gives me the entire circle. So this is half of the measure of the entire circle, half of 360. So it's always equal to 180 degrees. When two angles add up to 180, they are supplementary. The opposite angles in the inscribed quadrilateral are always supplementary. So here's some examples. They can start off very simple. Here we have an inscribed angle BAC. We want to find the measure of arc BC. Arc BC is the intercepted arc of the inscribed angle BAC. So the angle is half the arc, or the arc is twice the measure of that inscribed angle. So the measure of arc BC in this case would be 74 degrees. Over here, we want to find the measure of the inscribed angle, angle A, which intercepts the arc from B to C. I need to use the measure of a central angle, BOC, to see that this arc would be 132 degrees. And now the measure of angle A is 1/2 of 132, which is 66 degrees. Here, I want to find the measure of arc AB. There's several ways we can do this. We could use the inscribed angle BAC to find the measure of arc BC, times 2, which is 54 degrees. And then we see that we have a diameter, AC, so this is a semicircle. Arc AB has to be 180 minus 54, which is 126 degrees. You could also do this problem by working within this triangle and saying, okay, this is an isosceles triangle where the two base angles are 27, subtract those from 180, and you get this central angle, which is equal to the measure of the intercepted arc. In this diagram, we want to find the measure of angle C. And again, there's a couple different ways we could do this. We could use the 28 to say, okay, the measure of arc BC is 2 times 28, and then subtract from 180 to get the arc up here, and then divide by 2 to get C. Or quicker, if we look at this triangle, inscribed angle ABC is inscribed in a semicircle, which means this angle must be 90. So if I want to find the measure of angle C, it must be complementary to angle A. 90 minus 28 means this angle is 62 degrees. Now look at a couple more examples before we're done today. Here, I have two inscribed angles, and if I look at each one, here's my intercepted arc. And with the other inscribed angle, it has the same intercepted arc, which means that these two angles must be congruent. So I can write an equation setting their measures equal to each other, and then I can solve for x. So I'm going to subtract the 2x from both sides, add the 3, and divide both sides by 2. Over here, in order to solve for x, I need to again recognize that I have a right angle here because this inscribed angle is inscribed in a semicircle. If this is a right angle, the other two angles of the triangle have to add up to 90 degrees. I could work with these fractions here. I'm going to get a common denominator. This is 3/6 plus 2/6. So I have 5/6x. I'm going to subtract the 5. 5/6x equals 85. Multiply each side by the reciprocal. And I get that x is 102 degrees. One final example, we're going to do number 16 here, where we have this inscribed quadrilateral. The rule said that when you have an inscribed quadrilateral, the opposite angles must be supplementary. So here we can find x first. We can find x because x is an inscribed angle where we know that the intercepted arc is 108 plus 75. So x would be 91.5 degrees. Now that we have x, we can look at the angle that's opposite of x. X and z are opposite angles in the inscribed quadrilateral, so they must be supplementary. 91.5 plus z must add up to 180 degrees, which makes z 88.5 degrees. The other pair of opposite angles is both in terms of y. So when I add those two angles, the 2y plus the 3y plus 5, it must add up to 180. This is 5y. I'm going to subtract the 5, divide both sides by 5, and I get that y is 35. These diagrams can get more complicated with multiple angles in the same one, but we need to keep straight the relationship between a central angle, which is equal to the measure of its intercepted arc, and the inscribed angle, which is equal to 1/2 the measure of its intercepted arc.